around to it. I add it to my list. I will watch it.
Yep. Just kids bizarre adventure. Let's begin.
I will watch it. It's on my list.
Did we say pretty interesting?
Seems interesting enough that I might watch it. I'll watch it.
Do you know any other lectures that have? Do you know any other professors that are pretty good that happen at other times today? I'm trying to see if we can jump to another lecture for extra content for studying. Yeah.
I think Professor Gabriella is teaching. There's one other section.
Yeah, I'm trying to see if we could slide in between times. Between SI times.
I think there's only one other one.
I'm trying to hit as many essays as possible today at the same time.
All right, let's get started. Final exam next Wednesday, December 13, 10:30 a.m. Same location as usual, Elliott Hall of Music. Same seating location within the hall. Make sure you know where you're supposed to go. Just like before, if you get lost, look for your TA or look for me. On the course web page, I talked about on Friday, there's a set of practice problems. We'll go over as many of these as we can this week. Today we'll go over the first 10, 11 or so. There is also a final exam study guide. It's basically the study guides you've seen for the other two exams, plus some material from the first exam and things since the third exam put together. So it's a big, long document. Take a look at it. Okay, so again, that's the study guide posted on the course web page. All right, so like I said, we're going to go over the first 10, 11 or so of the practice problems that are on the course web page. All right, first one, a limit problem. This one is the limit as x goes to 1 of the function x squared minus 1 over x squared minus x. Okay, there are two ways to do it. There's the old way that we used to do by factoring and canceling, or if the condition is right, you could also use L'Hopital's rule. So let's see, if x goes to 1, upstairs is 1 minus 1, downstairs is 1 minus 1, right? So the old way we did way back then, in the beginning of the course, was to factor and cancel. And of course, the newer way, now you know L'Hopital's rule. All the problems that you've used to do this way that had 0 over 0 or infinity over infinity could be done using L'Hopital's rule. Let's try both of them. So the old way, we've got to factor things and find out what's causing that 0 over 0. Upstairs is a difference of squares, so it turns into x plus 1, x minus 1. Downstairs, pull out an x here, and then you see what's causing the 0 over 0. We get rid of that. And now when x goes to 1, we have a 2 over 1. That goes to 2. The other choice is L'Hopital's rule. We take the derivative of the top and the bottom separately, and then let x go to whatever number it wants to go to. And now when we let x be 1, it goes to 2 on the top, and downstairs is 2 minus 1. That's a 2. Okay, you get the same answer, of course. Either way you do it, it's the same limit, it has to have the same answer. Okay, nothing to this one. And by the way, there will not be extra emphasis on the material since exam 3. There might be an extra problem or two, proportional-wise, and maybe 1 or 2 fewer problems, proportional-wise, from the first exam material. In other words, we'll most likely steal a problem or 2 from the first exam and put a problem or 2 more on the material since the exam 3. I'll talk more about the actual spread Wednesday or Friday. Okay, problem 2. This one is a derivative problem. Y is x squared plus 1 times tangent of x, and we're looking for the derivative. Okay, so this is pretty straightforward. You use the product rule, simplify as much as you needed to match the answers. So nothing special about this. All right, product rule first. Derivative of the second. Derivative of tangent is secant squared plus the second times derivative of the first. And let's see. Yep, that looks like it. Looks like A, I think. So not much simplification is needed here. Okay. Number 3 is a continuity problem. You have a function that's defined as x squared plus a for x is less than 1, minus 1, sorry, and x cubed minus 8 for x is greater than or equal to minus 1. We're looking for all values of a so that h is continuous for all values of x. Okay, so first you look at this thing here. You got 2 branches of h. Both of these are polynomial functions. They are always continuous wherever they're defined. And that means the only place we have to investigate further is at x is equal to minus 1, when things break apart. Away from minus 1, that's always defined, whatever a is equal to. Away from minus 1 on the right side, that's always defined and always continuous. At x is equal to minus 1, for h to be continuous, we'll need 3 things to happen. First, h of minus 1 at the breakpoint here has to be defined. Second, the limit has to exist at x is equal to minus, as x approaches minus 1. Then lastly, the function has to be defined and the value has to be equal to the limit. Okay, so we'll have to check these 3 things to make sure things happen. The first one is easy to check. You look at the inequality here. The second branch is the branch for x is greater than or equal to minus 1. So we know that at x is equal to minus 1, we look at this branch right here. And we get minus 9. Okay? So the first condition is met. For the limit to exist, now we have to make sure the limit is the same, regardless of which direction you approach minus 1. If the limit from the left is equal to the limit from the right, okay, I check the limit from the left. From the left means we're looking at x values smaller than minus 1, and that refers to the top of the two branches. So we're looking at x squared plus a. And when x gets closer and closer to minus 1, smaller than minus 1, then this becomes closer and closer to 1. So this turns into 1 plus a. The limit from the right side, we're looking at the bottom branch this time, x squared minus 8. Rather, x cubed minus 8, sorry. And now when x becomes closer and closer to minus 1, this becomes closer and closer to minus 1. Minus 1 minus 8 is minus 9. So the limit is going to exist if these two are equal. We found out what they are. Now we make them equal. So this tells me x is equal to, a is equal to minus 10, right? All right, so this makes sure the second condition is met. Now the third condition. That's the second condition. That's good. Condition 3, now we require h of minus 1. From the first step, we see it's equal to minus 9. Function is defined to be minus 1. The limit is 1 plus a. Then we found out that if a is equal to minus 10, then the two one-sided limits are equal. Now using that a here, we see the limit is equal to minus 9. Okay? So therefore, if a is equal to minus 10, then h of x is continuous for all values of x. Okay? Questions? Okay, so the key part for continuity are those three things. The limit, the function has to be defined, and the limit has to exist, And also the limit has to be equal to the function value. Graphically, this means that there's no open circle, no asymptote, and no gap at -1 in this case. Moving on, number 4, evaluate the limit. X goes to 0 from the right-hand side of x times cosine of 1 over x. Here you're given a hint. Okay, the hint is useful because if you look at the limit right here, when x approaches 0, this obviously goes to 0. But cosine of any value always oscillates between -1 and 1. So cosine of 1 over 0 by itself, as x goes to 0, actually doesn't have a limit. And therefore, upon first glance, it looks like there's no limit here, because the second part does not approach any particular number. The first one goes to 0, that's fine, but the second one doesn't really go to anything. No, we use squeeze theorem. That's what this is setting up to do. So this right here, this tells us that we can use squeeze theorem. Because we know cosine of 1 over x is trapped between two things. If we know that is true, then squeeze theorem allows us to find the limit of this thing. Okay, so if we start with this thing right here, multiply by x on all three sides, we get negative x is less than or equal to x times cosine of 1 over x less than or equal to x times 1, and that's an x. Now we take the limit on all three sides as x approaches 0 from the right. And the middle one here, you can see, is what we want. Okay, now when x goes to 0, it becomes very close to 0. That's a continuous function. So we can just put in a 0 for x. The middle one, we can't do anything about it. But we got a inequality here to trap it in. The right-hand side, that's also a continuous function. So we simply put in the value of x in here for that x, and we get a 0. And now it becomes pretty clear what the limit wants to go to. It is always going to be between 0 and 0. And then the only thing that can be between 0 and 0 is 0 itself. Therefore, we see that this thing is going to have a limit of 0. Any question? Nope? Okay, good. Moving on to number 5. If the function is 1 over x plus 3, then we are looking for the limit as x approaches 1 of f of x minus f of 1 over x minus 1. All right. Now, one way you could do this is to substitute this function into here, subtract what it is equal to 1, and then try to work out the limit. That's one way to do it. That's fine. Another way is to recognize this as a derivative of the function. Remember, one of the definition of derivative is that one. We get this one from using the secant line slope by bringing the second point closer and closer to the first. So that's one definition of the derivative. So therefore, if you interpret this as a derivative of that function at 1, that's the other thing you could do. So limit as x approaches 1 of f of x minus f of 1 over x minus 1 is f prime of 1 with f of x equal to 1 over x plus 3. So you take one derivative, plugging x is equal to 1, and see what you get. You can use quotient rule here or use the chain rule here. Either way is fine. I'll take the derivative of this using the chain rule. Let's bring down the minus 1, keep the base, reduce the power by 1, so that's a minus 2, times derivative of the inside here. That turns out to be 1 in this case. Derivative of x plus 3 is equal to 1. So that's equal to minus 1 over x plus 3 squared. So now when we're plugging a 1 in here, we get minus 1 over 16. All right, so that should be the limit. Any question on this one? You almost never will want to use the limit definition of derivative again. It's not an efficient way to do it. Finding derivative using the various rules that you have learned, that's the way to do it. Now here you do need to remember, even though you're not really using it, but you need to remember at least the definition of derivative is that. And interpreting that as a derivative at certain value of x. Then you take the derivative and you do that. The original function. This thing? What do you mean? I mean, the other way you could do this is to treat it like a regular limit problem. And then you can simplify and try to make things work, canceling and factoring and all that. We'll use L'Hopital's rule, treat it like a limit problem. That's another way you could do it. That's probably not as fast as this, So you have your choices. It's just do things the smart way. That's really what it comes down to. All right, other questions on this one? If you use L'Hopital's rule, you're going to be taking the derivative of the same thing again. Anyway, right? So it really doesn't change too much. Okay, number 6 is one of those older problems we used to cover in this course, but we don't really cover that one explicitly anymore. So it's okay to skip number 6, but I'll talk a little bit about this. This is a problem about continuity of polynomial. It's looking for a root, and basically, if a polynomial is continuous, so they cannot skip over any value. If you can find out that this thing switches sign between two x values, then you know somewhere between those two x values, it has to cross the 0 point. And that's the root of the function. But like I said, we're going to skip that one. You don't have to worry about that on the exam. Let's look at 7. Okay, another pretty straightforward problem. Taking the derivative, plugging 1. Here we have a quotient, so we have to use quotient rule. Actually, you have two choices. If you leave the function as it was given to you, 1 minus x over 1 plus x, you can use the quotient rule. You could also rewrite it as 1 minus x times 1 plus x to the minus 1. Then use the product rule plus the chain rule. That seems a little bit more complicated than it needs to be, so let's stick with the quotient rule. But again, it's a choice that you have. Quotient rule, we take low, d high, derivative of the top, minus 1. Minus high, d low, derivative of downstairs is 1. All over downstairs squared. Simplify if you want to, but you don't really have to because you're going to plug in a value for x. So we'll just go and do it. Get the 2 minus 1, and that's a 0. Downstairs is a 2 squared. And so we end up getting a minus 2 over 4 or minus 1 over 2. The other one, quotient rule, product rule plus the chain rule, it's about a little bit longer than this one. This one is more direct. But it's a choice. You know lots of rules now, so you have lots of choices. Number 8. Number 8, we're looking for the derivative of natural log of 1 minus x squared plus sine squared of x. You got to be really careful with the way we give powers to trig functions. That power of 2 goes with the sign, so that means this is sine of x, the whole thing squared. If the 2 were to go with x, then that's an entirely different thing. That means sine of x squared. Okay, so be careful with where the power is placed. All right, now we take the derivative. Natural log of something has a derivative that's equal to 1 over that something times derivative of that something. Okay, that came from the chain rule. 1 over something, derivative of that something. Second part, same idea. We got something more than an x raised to the second power. By the chain rule, we get 2 times the same base, reduce the power by 1, times derivative of that, cosine of x. So that again is from the chain rule. Remember I said about chain rule, if you ever wonder if you have to use chain rule, that probably means yes, and you can always use the chain rule even when you don't have to. Use the chain rule if you're ever in doubt. What's that? When in doubt, chain it out. Yes, I remember. I said that. Okay, so what do we get? We get this thing here. Okay, and it doesn't look like you're asked to simplify, nope, anymore. There's really nothing else you can do to simplify. That's what it is. Okay, so like I said, be very careful with the placement of the power. So what did I do? What did I do? So this, the 2 goes with the sine, so that means sine of x squared. This one means sine of the thing x squared, right? The derivatives, of course, are very different because there are different functions. All right, number 9. We're making good progress. Second derivative of 1 minus x over 1 plus x. Isn't that the same thing we did in number 7? Yeah, it's the same function, so we'll just borrow that from 7. From number 7, the first derivative, so I still had to simplify that thing. Okay, so we got that from number 7. It's the same function. Now we simplify this a little bit. We get 1 plus x minus, be careful with signs now, minus 1 plus x all over 1 plus x squared. The what? Oh, that's right. Yeah. The whole thing should be negative. Negative, sorry. And I just said be very careful with the signs. And look what I did. Okay, so I think that's right. Upstairs, the x's go away. We have a minus 2. Now Now remember, if the top is a constant, it's always easier to handle by rewriting it this way. Bring the thing downstairs up instead of using quotient rule again. It's always better this way. All right, so that's the most simplified form of the first derivative we got. Let's take derivative one more time to get the second derivative. Here we'll get minus 2 times, bring the power down, keep the base, reduce the power by 1, times derivative of that thing, which in this case turns out to be 1. So we get positive 4, 1 plus x to the negative 3. In quotient form, this would be 4 over 1 plus x to the positive 3. Okay, and if you want a third derivative, that's also pretty easy to do. This thing really doesn't get any more complicated than that. All right, moving on. Number 10. Given a function that defines y implicitly, and we're supposed to use implicit differentiation to find the derivative of y. So here we're told that y is an implicit function of x. We don't know what it exactly looks like, but we know it depends on x. And so therefore, when you take the derivative, this guy right here is a product of two functions of x. You have x that, of course, depends on x, and you have y squared that does depend on x. We don't know what it looks like, but we know it does. And therefore, when you take the derivative on both sides, the first part here needs a product rule. Okay, so we get first times derivative of the second. The second is y squared. We use the chain rule here, bring the 2 down, reduce the power by 1. And then y is a function of x. So by the chain rule, we need to multiply by its derivative. That's the first part of the product rule. First times derivative of the second. Now we get a second part. Second times the derivative of the first. 1. Next term, simple, minus 2x. Y, we don't know what it looks like, but its derivative is y prime. And 5 is a constant, derivative is 0. Right-hand side derivative of 0 is a 0. So we get that. Okay, our goal is to find y prime, so we put everything that doesn't have y prime on the other side. We have two things containing y prime. First term is 2xy and y prime. That also has a y prime. We keep it on the left. We don't want this, we don't want that. So let's move this over to the right. Move that over to the right. Factor out y prime. And finally, to find what y prime is equal to, we divide by that excess stuff. There we go. Oh, we want to find y prime at minus 2, 1. Right. Okay, so at minus 2, 1, that is x and that's y, right? So y prime is equal to minus 4 minus 1. It's a minus 5 on the top. Downstairs is 2 times x minus 4 plus 1 minus 3. So 5 over 3, is that right? Looks right. All right, be very careful when you do implicit differentiation. Every y is really something with an x in it. Derivative of it, basically every time you deal with y, when you take the derivative implicitly, there's going to be a y prime somewhere for each y that you differentiate. Find the maximum and minimum values of the function f of x is equal to 3x squared minus plus 6x minus 10 on the interval minus 2 to 2. Okay, we got this function here. On that interval, we're looking for the max and min. If you're given a closed interval here, that's what we got. That means we're looking for the absolute max and the absolute min. So what you do is you find the critical numbers and then you compare to the value of the of the function at each critical number to the value at the end points. So let's first find the critical numbers. 6x plus 6 equal to 0. And so that means x is minus 1. Another thing to look out for is that we got to be careful and make sure that this is inside that interval. There could be multiple critical numbers. You just throw out every single one that's not inside the interval. And that one is between minus 1 and 2, so we keep that. So now we compare the function value at the end points. Left end point, critical number, right endpoint. Be careful to use the function itself and not the derivative. We care about how high and how low the y value is, not the slope anymore. The slope helps us find the critical number, but we really care about the value of that function. Plugging minus 2 into here, we get 12 minus 12 minus 10, so that's minus 10. Plugging minus 1, we get 3, minus 6 minus 10, so that's minus 13. Plugging positive 2, we get 12, plus 12 minus 10. 24 minus 10, that's 14. This is our absolute max. And this is our absolute min. Okay? So that's how you find the absolute max and min. Critical number compared to endpoints. Pick the highest one and lowest one to be your max and min. Okay, we got time for one more, so let's do 12. For a differentiable function f of x, it is known that f of 3 is equal to 5. And f prime of 3 is equal to minus 2. Use a linear approximation to get the approximated value of f of 3.02. Okay, so you need to remember at least how to get the formula for linear approximation. And remember, all this thing is this equation of the tangent line at x is equal to a. If you know how to find the equation of a tangent line, then you have the linear approximation. They are identical. They're exactly the same thing. Here, a is equal to 3. That's what these two things are telling us. We know the function value at 3. We know the slope at 3. So f of x is going to be roughly equal to f of a, f of 3, plus f prime of 3 times x minus 3, which is roughly equal to, we know that's a 5, that's a minus 2. And therefore, to find f of 3.02, plugging into that formula right above, (3.02) minus 3 is 0.02, so this is 5 minus 0.04, which is therefore around 4.96. Okay, so we got through 12 of them. We'll continue this on Wednesday and Friday. And if I find other problems I think are relevant to your exam, I'll be sure to go over those too on Wednesday and Friday. All right, that's it. See you Wednesday.